that you have to draw. So there is a member here. That member here is under the member sitting here. Look at it. I have to put equal and opposite. I must have mentioned this at least 4 or 5 or 6 times in class. So if you put this in tension and this put the tension, you have to be careful about it. That means if this is the tension, this rod should be going up. This is not going up. It's not possible even. But remember that if you put it in tension, at least the answer should come negative. Is that correct or not? So if you do it correctly. And then I did not use the theta. Of course, you can use the theta. This is tangent, tangent, theta, but they are using this theta. They are using, I don't know, point, whatever I gave you, 1 theta, 3 theta, 4 theta, as some of you use, which is acceptable. There is nothing wrong with it, but I showed you a better method, which correctly, it's much longer. Everybody understands. Theta is the same as ratio. Yes, but I used the ratio. I show it to you. Now, what we want to do is this. First of all, the static of this, notice 1, 2, 3, and 4. As soon as you have 4 unknown, it is not solvable because you only have 3 equations of equilibrium. However, the way I did it, I said get rid of dx and dy by taking moment about point D. Yes or no? Correct? So this is what we did. Exactly all your homework was the following. You should have all done it if you did the homework correctly, which I'm giving you back to you. There are see lots of 20s there, 20 out of 20. So I assume you all have done those homework. Please, for the next set of homework, difficult to handle, you have to put more energy into it. You can do it, but you have to put more time into it by understanding the principle, not the procedure. The procedure is the following. Sigma m at D equal to 0. Which gives you 62. It's very simple. You set 62 times 4 meter going this way, which is positive, minus F1 times 3 meter, minus F2 times 1 meter equal to 0. Or it could not be any simpler than that 3F1 plus F2 become equal to 248 kilonewton, because meter and meter drops out. So some people put here kilonewton meter, which is still correct technically, but this is becoming meter and meter drops out from both sides. Is that understood? So it becomes 240 kilonewton, the sum of the two forces. If I come up with another relationship between F1 and F2, then I'm going to be able to solve it. Remember, of course, you have sigma Fy equal to 0 and you have sigma Fx equal to 0, but that's not going to help you. Still, you have 3 equations and 4 unknown. Now, some of you, after all of this, this didn't work, then take the moment about A, then take the moment about B, take the moment about, you keep doing it as if you do that again and again, the problem is going to be solved. And I have mentioned that in class. I warned you about that. Don't do that. Otherwise, you get the Nobel Prize. Remember that? You all laugh about it. So still few people, I don't know, in this class, the other class, doing it. That's not the key. The key is this problem is indeterminate problem. The entire, your homework was all about indeterminate problem without any exception. The homework that I just returned to you was all about indeterminate problem. This was the simplest one that I could find there. So here it is. This is going down. So in other words, this rod, which is sitting here, going to be going down here, which is going to be expanded. So it's going to, so this will be delta of the rod 2, and this BB prime will be equal to delta of rod 1. And this is how much point A is going to move down, which I asked you, do not call it delta, remember? Because there is a rod here. Remember, the rod was sitting here. I don't want to show it yet. The rod was sitting here, yes or no? Now it becomes this much smaller. So that is the delta, yes. Here, this rod was sitting here. Now it's stretching it down here. This one will be in tension. Everybody noticed that, most of you actually. By the way, there are at least about 10 people are getting 20 out of 20. I'm not complaining about those because this problem was in such a format that everybody should get at least 12 and above. Everybody, that's what my board is about. If you are not getting it, that means you are not paying attention to the detail. You are concentrating on some sort of, I don't know, solution manual or some idea which is not presented here. Nevertheless, look at it. This is 1 meter, yes or no? And this is 3 meter, yes or no? This is the simple geometry that you have to use. This, if this is 3 to 1, this must be 3 1. Is that correct or not? Yes, that must be 3 to 1 as well. Yes or no? Yes? 3 to 1. This must be 3 to 1. That's the ratio I'm using that. So therefore, delta 1 must be 3 times of delta 2. Correct? Yes? No theta, no this. If you use the theta, at least learn what is that they are doing there. And if you're learning it properly, you should answer that question properly. But that system is much longer. This is much shorter. Of course, delta 1 equal to 1. Delta 1 equal to F1 L divided by EA. Yes or no? Correct? But this is the second relationship that I have to use. Many of you people, after all of this, again, they use delta 1 equal to delta 2. How can that be possible? Delta 1 is here, delta 2 is here, this is a rod. I mean, I have no clue if people mention that in the quiz, what is their line of thinking? Is that understood what I'm saying? What do they think? What do they see is very important. How can this delta become this delta? They put it there, they show it there, but when they write the equation, they put these two equal. Yes? That is impossible to understand even for me. Nevertheless, writing this equation in the formula, because each delta equal to PL over EA. But what is P here? P here is F1. So all you have to do is the following. F1 times L. L was equal to 0.8 meter. Given to you, yes or no? Divided by EA. E was 80 G Pascal times 10 to the power of 9. Multiplied by area. Fortunately, area is the same. So if area is the same, area is going to be eliminated. But however, we have to put it there in order for the future understanding. Now, I give you the area equal to 600 millimeter square for both classes. They have different questions, totally different. But I gave the area the same to just see that. How many students do you think that when they converted that to the meter, made a mistake there? Just give me, out of 100 students. 48 on each class. How many people do you think they made mistake? 1, 2, 3, or 1/3, or half the class? Half the class, yes. Half a class are making mistake converting 600 millimeter square into meter square. They divide that by 10 to 1,000. 1,000 is for 1 meter. This is meter to the power of 2. So you have to divide that by 10 to the power, 1,000 to the power of 2. So many people put it like that. Look at all you like that. Is that correct? Of course, it's not correct. Because you are not paying attention. That's all I can tell you that. You know that. You should not be, you are not doing your homework correctly. You are not even there to do this kind of problem 100%, and that's where the mistake is. You have to divide that by 10 to the power of minus 6, because it's a meter square or millimeter square. Nevertheless, that kind of mistake is what? That is delta 1. Must be equal to 3 times delta 2. So you put the 3 there not to forget, because I'm using this formula now. Delta 2 is F2. I have to go a little faster, otherwise I cannot finish the lecture. The length was this time 0.90 divided by E, which was 120 times 10 to the power of 9. Times the same A. Some people smartly, they put A here, they put A because they notice that A is going to be eliminated. By the way, if you make a mistake here, you make this mistake there, that mistake also eliminates. So in this case, you are okay. So this A and that A is going to drops out. This and that actually going to drop out. So this is 80. I made it very simple for you, divided by 80. If you simplify that one, any other item, at the end you get F1 equal to 2.25 F2. That's all you need. Between this, there is no theta. It is so clean and so nice. These are all in the same order, so if there are lots of number drops out from this. So that's all you need. Is that correct or not? F1 equal to, now, I have two equations now. Equation 1 and equation 2. Yes? Correct? So you put that there. So that equation become, after F1 you calculate the F1, it become 3 times 2.25 F2, because you're changing F1 to F2 now, plus F2 equal to 248. You don't have to use all those. Some of you end up with 10 to the power of minus 15 because all your unit is wrong. So many of you are not paying attention to the kilo, mega, and G. There are different numbers there. Some of them are in K, some of them are in M, some of them are in G. Yes or no? So you have to keep track of all of that. That's why you end up, some of you, to numbers 10 to the power of minus 11, minus 15. I have all as high as minus 18. I don't know. Okay, those are all wrong numbers. Is that correct or not? Yes. None of them needed, so that's you just put this there. You solve for that for F2. F2 become, actually, I gave you very round numbers, 32 kilonewton. And F1, which is 2.25 times that, become equal to 72 kilonewton. Many of you got that one correctly. After that, the rest is easy. The rest is a throw-in. This is back to square one. So the main part of the problem was these two parts. Is that correct? Writing the free body diagram and showing the picture, showing me how that deflects. Is that correct? How that's going to go down. The rest, again, is very simple. Again, you have to be very careful. Sigma 1 was equal to, actually, lecture 1. Sigma 1 equal to force over area. Not many points there. Remember that. All the points are here. And part 3, which is similar to part 1, is that, or the last part. Is that understood? This part, I just wanted to see what you do watching the unit. So here, F1 is 72, so you have to put, okay, by the way, now here, by the way I have put it, this is in tension, this is in compression. Many of you did not do that. So sigma 1 actually is in negative. So please be careful, because that's very important for epsilon, etc. So this is 72,000 Newton divided by 600. Here you have to be careful. Here your mistake will not be eliminated. I have done that in class. Actually, all I ask you to do, forget about this. That's your mega. Because when this go to the numerator, become 10 to the power of 6, and that's your mega. 72,000 divided by 600 is very simple. It becomes minus 120 megapascal. This is your mega. As simple as that. And then you calculate sigma 2. Sigma 2 also is equal to plus, because that's the tension. So that's the tension. Sigma 2 was 32,000 Newton. This is Newton, and this is Newton per se. So divided by, again, the area was the same area, 600 times 10 to the power of minus 6. So this one becomes equal to 53.3 megapascal. Now notice some of you write 53 wrong. You should go at least 3 digits. Some of you put here 5, 6, 7, 8, up to 8 decimal point. Wrong too. Why you are wasting your time? We are carrying everything to 3 digit accuracy. I mentioned that. We mentioned that in the static. That's all the engineering work will be done in that format. So notice it's 3, 3. So next is epsilon. Now some of you want to calculate the epsilon. Still you are looking epsilon equal to delta over L. Wrong. You already have everything in front of you. Epsilon is, yes, epsilon equal to delta over L. But epsilon at the same time from Hooke's law is equal to sigma divided by modulus of LS. So why not use that? Because today's lecture or this week's homework is all about that. So epsilon 1 equal to sigma 1 divided by E1. Sigma 1 is minus 120 times 10 to the power of 6. Divided by E1, I don't know how much it was, 80. Yeah, 80 times 10 to the power of 9. Notice all this cake, this has to be used in your system. Some of you even don't show the result there. I need to see that to see where you're making the mistake. So anyhow, this becomes equal to minus 1500 micro. Micro is 10 to the power of minus 6. Again, they are not using that in the solution manual, but I ask you always, I appreciate that many of you did, to calculate your epsilon in micro, not in 0.00015, because you are making mistake there. Negative, because it is in compression. And epsilon 2, the same thing, equal to sigma 2 over E2, so we can make it that shorter because you have everything there. So epsilon becomes 444 macro, and it is plus because it is in tension. Then I ask you the last question, which is related really to first one. If you did the first one, the last one is very simple. The last one is, what is the displacement of A? That you should not call it like solution manual. That's not, there is no rod here. Everybody, I showed you here. There is a rod here. It's compressing this much. I mean, you're going down this much. There is a rod here, but there is nothing here. That I said, it's better. I don't subtract point from you. It's better to be called capital delta. A small delta usually is related to the deformation of a rod. Is that correct or not? Yes? Those delta that you see there originally, one was the deformation of rod 1, the other one was the deformation of rod 2. There is no rod here, everybody. The rigid bar at the middle goes down at A. Is that correct? That's technicality. Don't worry about that. So all you have to do, either calculate delta 2 or delta 1 or use the ratio. Is that correct? However, how do I calculate delta? Again, don't use delta equal to PL over EA. Epsilon, again, remember, is the amount of deformation per unit of length. Yes or no? Correct? So can I calculate the delta? Delta equal to epsilon times L. It's as simple as that. Yes or no? Remember what we had discussion we had in class, in the office hours? Might as well mention it to everybody. For a couple of students who are still look of epsilon as a sort of magical number, something they cannot grab the idea behind it, we have the discussion. I suddenly remember to ask a question. I said, what is the difference from you and somebody else? Actually, one person came after you. I said, what's the difference between weight and the density that all of you have learned it in high school or somewhere? What's the difference? Can you explain to me? What's the difference between density and the weight of an object? What's the density? Is the amount of weight for 1 cubic inch, yes? And then if you want to calculate the weight, what do? You take the density multiplied by volume, yes? Epsilon is the same thing. Epsilon is the amount of change for 1 unit of length. So if I have 10 units, I have to multiply. So if you understand epsilon, the meaning of epsilon, you should be able to put all of this together, including today's lecture. Notice now what you get. You see, epsilon, what is epsilon? Epsilon, I keep saying that, but you keep looking at epsilon at sigma over E or delta over L, which is wrong. Epsilon, like a rho, has a meaning, and that is the one has to be registered. That's the word that gives you all the ideas. Epsilon has a meaning, sigma has a meaning. Sigma is the amount of force per unit of area. If I have larger area, I multiply it by area. Everything comes to you, not other way around. You are all guys still concentrating on the formula, not the idea. Look at today's lecture after this. Please pay attention to the detail. All the example I do is irrelevant when you look at the idea first, learn the idea. Is that understood? As simple as that. Now you all smiling. See that? You say, oh, that was what epsilon I was doing. Epsilon is the amount of deformation for 1 unit of length. I have to multiply it by length. Is that understood? So that's the delta. Nevertheless, making the story short, you can calculate delta 1 or delta 2. Delta 1 is minus 1500, means it goes down, as you see it there, times 10 to the power of 6. What was the length of it? I don't know whether I calculate delta 1 or I calculate delta 1. Delta 1 length was how much? Delta was 80.8 meter or 800 millimeter. Is that correct or not? So 800 millimeter, so it becomes equal to minus 1.2 millimeter. So that means the delta 1 becomes 1.2 millimeter going down. So if this is 1.2, some people calculate that one, which is 1/3 of it, by the way. If this is 1.2, this must be 1/3 of it, yes or no? So that becomes 0.4, and how much is that one? That you use the ratio again. Is that correct or not? So therefore, I put it here now. Delta at B is equal to 4 over 3, because this is the ratio of the 4 over 3 of 1.2. Of 1.2. You can put it negative if one, because it's going down, but it doesn't matter. So minus, so or it's going down equal to 1.6. So right, by the way, this is 0.4, this is 1.2, this is 1.6. So you can now calculate your theta if you want. Theta is become 0.4 times 10 to the power of minus 3 radian. Yes? All right. Everybody okay? Look how much time I spent explaining this simple problem to you, which was done. Go to your note. This problem exactly with the same ratio was given to you. I did it in class for you. There's another item that you want to make. Now let's go to today's lecture. Now please pay attention. Today's lecture is very important because we are going to finish this chapter. Hopefully on Thursday we are need your new handout, and we are going to move into next chapter, which is for the first time we do engineering work, and that is the torsion or the shaft design, which is totally different, a little bit more sophisticated than this. But so far, this is what we said last time, which is the idea. Now, I want you to understand that we have talked about a series of numbers, and those numbers, what we talk about the sigma x, we talk about epsilon x, we talk about modulus of elasticity, and we talk about, last week, we talked about Poisson ratio, which was very important. The idea, again, is that you should understand the meaning of the nu. Is that correct or false? If you do understand, you write your own equation. Then I did this, going back again to what I did last time in order to refresh your memory, and this is the way you should look at it. You should not remember this equation. You should understand the meaning of nu. What's the nu? Now, somebody explain it to me. Don't tell me the nu is a formula I gave you. That's no good. The nu has a meaning. What's the meaning of that? No idea. See, that's the whole thing. You have to go back to your note. Whatever strain you are creating on one direction, nu percent of it goes to the other direction. The idea was this. The idea was that when I pull this way, the other side will become smaller. But remember, this has, let's say, 24-inch length. This has only 2-inch length. So I cannot go by the length, everybody. I can go by epsilon. I'm creating an epsilon here. According to the definition, nu percent of that goes to the other side. Yes or no? In the y, if this is x, nu percent goes in the y direction. Nu percent goes to the z direction. That means if I have a plate here, and I put that under a sigma x here, this is sigma x, which we call it uniaxial loading. This is like the rod. This is now becoming a plate because you see this is a plate, this is the plate. Body of your car is a plate. Whatever you see is a plate. This monitor is a plate. This is a plate. It has a length, it has a height, and it has a depth, everybody, or thickness. Is that got 3D body? Is that correct or not? Now I'm putting only sigma x. According to so far what we learned, we can calculate, of course, if I give you the P, you divide the P by the area of the cross section to get, I do an example, you will see that. To calculate the sigma x, is that sigma x is force over area. I have to give you the force, I have to give you the area. We can do that later on. Is that understood? Yes? However, I'm creating a sigma x. This is the idea I presented to you. Therefore, according to the Hooke's law, I can have an epsilon x equal to, that's why I said concentrate on that one. That epsilon x means the amount of deformation for 1 unit of length along the x direction, correct? Now, does this affect the other two? Everybody has to say yes. Is that how much effect does it go on the other side? Nu. So in other words, if nu is 0.2, 20% of this goes to the other side. So as the result, I have going to have an epsilon in the y direction and epsilon in the z direction, because the object is 3D now, x, y, and z. You need to put that there. Is that correct? Your stress is in the x direction. Therefore, I said, as the result, this is the black stress. As the result, you have epsilon y and epsilon z, which is nu percent of that. Of course, it has to be opposite. Why opposite? When this is the tension, the other side becomes smaller and smaller. When this is compression, the other side becomes larger and larger. So it's a negative. So I have to put minus, okay, nu percent of this. Let's say that nu is given equal to 0.2. You know that 0.2 means? That means 20%. Is that correct or not? So minus nu sigma x over E minus nu sigma x. Whatever I created in the x direction, nu percent goes to the other two directions, correct? But this, if this was a one-dimensional loading, this is what I get, which is true for the rod or two force member. That's all I need to worry about. Then I can put delta equal to PL over A. As soon as I change this to two-dimensional body, x and y, then I said, okay, let's forget about this one. Let's assume there is a sigma y on this object, which is, this is a plate. I'm pulling it this way and pulling it that way. Yes or no? Now, what is the original? Forget about it, as if this is not there. Right now, the stress is, the whole thing should be written in the y direction. So I have created a sigma y. So what is epsilon in the y direction? Epsilon in the y direction becomes sigma over modulus of elasticity, but this is not sigma x. This is sigma y. So I have, where should I put it there? Not here. I have to put it here. Is that correct or not? Plus sigma y over modulus of elasticity according to the Hooke's law. Is that, I'm doing the same thing. Instead of doing it for x, I'm doing it for y. Everybody, and like I'm pulling it this way. If I pulling it this way, the other two sides become this, but this is the y direction. X and z become, this is the z, this is the, I'm sorry, this is the x, this is the z, this is the y. If I pull this in the y direction, it's going to affect my x and z, correct? So here I'm pulling it in the y direction in the form of tension. Nu percent goes here. Nu percent goes there. Is that correct or not? Notice I'm doing all of that not because I'm remembering this formula. I'm doing that because all the value of nu. Is that understood? So now that you look at it, if this is tension, this is the tension, this side should get twice smaller. Look, smaller and smaller. Is that correct or not? Yes? Correct. Finally, I said, if we usually don't have that, I said if there is a possibility that you have a sigma z this time, or which makes this a three. Look, we went from one-dimensional to two-dimensional into three-dimensional, because if you look at the soil or you look at any body, solid body, if you go under the ground, the piece of, look at the one point there, the sigma is coming from x direction, y direction, and z direction. Everybody, the bodies are usually 3D, but we treat them differently. Is that understood? We treat them in one-dimensional or two. This, I said, one column is one-dimensional, two column is two-dimensional. Now I'm making it into three. This time I have to put sigma z here, sigma z over E, as if I'm stretching it this side, and nu percent goes there. So this is called generalized Hooke's law. Everybody understand that? Yes, because it takes into account all three sigma if they are all there, which sometimes they are one of them, sometimes they are two. Look at some of your problems. Some of your homework problem are the rod, so it is one-dimensional. Some of them are a plate, two-dimensional. We rarely go to 3D at this time. Everybody understand, unless there is some specific meaning which I'm going to explain to you at the end of the class. Is that understood? Yes? But we never do 3D analysis. Remember that. Yes? We only go one or two. Is that correct? Yes? So we have to use one column or two columns. You want to do that. I ask you to do that. Each column individually, look, if I hold this one like that, this is this black column. Yes or no? But if I hold it like that, it is only the purple. Everybody see, everything is in the white. If I put it like that, this will be the red one. Is that correct? However, if I have this plate, which has black and purple, then I have to use this too. Is that correct? But if I have all three of them, I have to use all three of them. Occasionally we do that. Is that okay or not? Now let's go to an example. Now before I go to anything, because I don't want you to lose this one. So quickly, let's go to an example, which is very simple example. And through example, I'm going to show you a few more ideas there. Then this example related to this problem. This is generalized Hooke's law. All these are normal strain, and these are normal stresses. So therefore, we have all of this being explained to you. Is that correct or not? Now look at this plate, guys. So we have a plate here, 10-inch wide, 8-inch the height, and we have a thickness of 2 inches. And then we have a force here somehow applied in that direction, which I'm going to put uniformly distributed over the area, but I'm not showing that. This force is being uniformly distributed over the area, and that force is equal to 320 kips, or 320,000 pounds applied there. And then I have here also similarly both in tension. I can change it to compression if you want for some of your homework. Remember, they are in compression. So also going that way in the y direction. So we have to assume always an x and y z. It's not given. You have to assume the standard word. Sometimes we change that for just to see whether you can understand the system or not. Okay? The question is this, guys. You don't have it in your handout. I don't believe you have it. You want to calculate change in the length, height, and thickness of this plate. Change in the length, height, write it down, and thickness of the plate. There are a couple of other questions. I will explain it afterwards. I don't want to bring it all together. Notice I cannot use, again, delta equal to PL over EA. Why? I mentioned that this is the 4th time I'm saying it. Even today is the 3rd time I'm saying. Why? Because that is only for 1P. There are 1P going in the X. There is 1P going to the Y. Then they are going to interact each one. So therefore, I have to calculate the epsilon, which is the amount of deformation per unit of length in the X direction, Y direction, and 0, because I have several loads. Everybody understand that. PL over EA is only good. I put it here. PL over EA for delta is only good, which you have a rod, a 2-force member. Everybody understand, which was the lecture 1 and 2. Yes? 1st week, 2nd week. Now you are in the 5th week. Remember that? Yes? Okay. You are a little bit behind. You have to catch up. Now, what is sigma x now? Let's calculate sigma x, first of all. We have here, of course, 2D, so I don't have to worry about that. There is a sigma x and there is a sigma y. There is no sigma z. Everybody see that? So sigma z here, what's sigma x equal to? 320 kips divided by what? What area? Of course, I have given this problem, and the student made that mistake. That is back to lecture 1. What area? 2 inch by 8 inch. The cross section perpendicular to that load is that's what the definition of sigma is. Perpendicular. This is perpendicular to this plate. Yes or no? That's the area which is resisting that load. Correct? Yes? As we have done it in the past. So 2 times 8. If you don't get this one, you have to go back to lecture 1. I'm sorry to say that. And I have had this had happened in the next quiz, the type of quiz I give you. That's just 2 by 8 definitely. Is that correct or not? Yes? And therefore, that's 20 KSI. This is inch square, so this becomes 20 KSI, which is kips per inch square. Still, some students do not understand that idea of KSI versus kips. Kips is the 1,000 pound. KSI is kips per inch square. Everybody understand? Kips per inch square. Then sigma y also is equal to, obviously, 200 divided by what? 200K divided by what area? This time we are talking about that area which is 2 by 10 by 2, because that's resisting that area, 2 by 10. So it is 10 KSI. So this plate is under 2 tension, one in the X direction, one in the Y direction. Obviously, in order to calculate the change in the length, I cannot use delta, because this is biaxial. I have to use this. Is that correct or not? Yes? So what's epsilon x? Now I put here epsilon x equal. Epsilon x, I've just put it there. I don't have to repeat it. It's sigma x over E minus nu sigma y over E. Everybody understand what you are doing here? Now, technically, this is what you are doing here. You are pulling it this way, yes or no? But as the result of this pull, this side must be a little bit getting smaller. And that's it. You see, plus and minus. Everybody see what I'm talking about? It's very simple. It is there. You have to understand what you are doing. So it is 20 KSI divided by, oh, I have to give you, I'm sorry. So for this problem, I have to give you E, and I have to give you mu Poisson ratio and modulus of elasticity. In other words, it doesn't work. This is some kind of aluminum, so it is 10,000 KSI. Sometimes we give you in PSI, so you have to watch out for the unit. Don't do the same thing as you did in your quiz. And the nu is 0.25. So whatever you're creating in one direction, 25% goes to the other side. Yes? With negative format. So 20 divided by, this is epsilon x, which is 20 divided by 10,000 KSI. So epsilon doesn't have a unit. So KSI over KSI, so okay, minus 0.25. Sigma y over E. Sigma y is 10 divided by 10,000. So let's calculate that one more time. So what happened here? This become equal to 2,000 micro, and this one become minus 0.25 of 1,000 micro. I put it this way in order because we don't want to repeat that. So epsilon x becomes 2,000 micro. This is micro also. Minus 250 micro, so it is 1,750 micro, and it is plus means it's going to be expanded. Yes or no? Correct? So immediately now you can calculate delta L. Delta L, now this is the amount of change for 1 unit. Now how many units do I have? 10 inches. Yes, sir. So all I have to do, delta L become 1,750 micro, which is 10 to the power of minus 6, times the length. The length is 10 inches. So therefore, I get 0.017. Notice this is very small quantity. It's 100 of inch, but it's still there. Yes or no? Now, can I calculate the change in the y direction? Yes, I can. So this time I have to calculate epsilon y. Again, remember, you cannot use PL over EI because two action there. Is that understood? Yes? Epsilon y, similarly epsilon y. So epsilon y, now this time look what it is. It is minus nu sigma x over E. I already have sigma x over E. Sigma x over E is 2000. Yes or no? Correct? This is epsilon here. So it is minus 0.25. I don't have to repeat that. 2000. Yes or no? And then this one become plus sigma y over E. Sigma y over E is 1000 plus 1000. So therefore, this becomes 1/4 of that, which is 500 and 500. So I should end up with plus 5. This becomes minus 500. This becomes plus 1000. So we end up with plus 500 micro. So in the y direction, we have also expansion of 500 micro. Therefore, we are going to calculate delta of the height. Delta of the height then become equal to 500 micro, or 500 times 10 to the power of minus 6. How much height how many units do we have? We have, this is the change for 1 unit of height because it is in the y direction. And I have 8 units there, 8 inches. Therefore, there is a small quantity of 0.00. Notice in some of your homework, they ask you to calculate change in the length AB, then they calculate the change in the length BC, that sort of. That's the same thing. Is that understood? I just want you to see that I refer to X and Y in general, but in the book they say A, B, B, C. Is that correct? And is there a change in the thickness of this plate? Of course, it's going to get much smaller. So I should get 2 negative. Everybody see that? Because this is tension, it gets smaller. This is tension, it gets smaller. As you see here, negative and negative. Remember, if sigma x is compression, so it becomes plus, so become minus. Minus times minus become plus. So that takes care of by itself. So this is valid for tension and compression as well. So anyhow, epsilon z, I don't have to calculate that because, again, the numbers are here. For this one, I have minus 25. See, we already calculated of 2000. For the other one, we have minus 0.25 of 1000. So you calculate that together. Both of them are negative, so it becomes equal to minus 750 micro in the z direction. It's negative because both have the effect of negative. And finally, we can calculate the delta of the thickness. Delta of the thickness is equal to, again, minus 750 micro, or 10 to the power of minus 6, times the thickness was only 2 inches. So we put 2 inches. Now, notice if that become a rod like that, the other two are equal. Everybody understands because they have the same dimension, they have the same epsilon. So some of your homework is there. Anyhow, you calculate that one equal to minus 0.0015. Now, this is the result of using generalized Hooke's law. It is in your book. It is still in chapter 2. You should concentrate on that one. Now I'm going to add 2 more parameters that we did not talk about this before. One is the change. You should open your handout. It's at the end of your handout. Now, before you look at it, let me explain to you what you should do and what you should not do. If I ask you to find the change in this area, what do? What's the original area? The original area is 10 by 8. Yes? This has changed. 10 has increased. 8 has increased. How much increase do we have? delta and delta. Everybody see that? This is the amount, mark it down. This is the amount of change in the x direction. Yes? Not epsilon, delta. That is the amount of change in the y direction. Technically, anybody at this stage of math, if I ask you to find the delta A or the change in this, so you say, okay, I have an area originally. Now I have a area new, so I would subtract that from each other and I get their number. Yes or no? This is logical, and this is logic is correct. Yes? However, this is what's going to happen. Now, what is going to happen is if I want to calculate dA this way, this length, the original length is 10 inch by 8 inch. The new length is the following: 10 point what? 10 point. I'll put it there for you to see. 0.175. Yes or no? Everybody see what I'm talking about there? Correct? That is how much change delta we had. Yes or no? So after deformation, 10 inch become 10.017 multiplied by 8 inch plus. 8 inch how much? 8.004. Yes or no? Minus 10 by 8 original length. That is the change in the diameter. Would it work? Maybe, maybe not. If you carry your calculator to a 12-digit decimal point, maybe you get an answer there. Everybody see what happened here. This is very important to recognize that. This number times this number, because look at this times that. Look how small that becomes. Is that understood? When you add it together, and we are carrying everything to 3-digit accuracy, this effectively, if you do it that way, the way I asked you to do it, because some of you do not, that this becomes 80 minus 80. Is that correct? Because there is two small number added to a very large number. As an example, this is what we do in real life, as I said it many times. When you call it about distance from here to San Francisco, you don't call it in inch, because if somebody really goes there, there is a difference between 5 inch between there and Oakland, maybe, I don't know, or whatever. But you call it in mile, yes or no? Mile is so many inches. Or you talk about the wealth of somebody, you go to the Bill Gates, you say 556 billion, right? So you don't consider even the million, you don't consider even the thousand. Everybody understand what I'm saying? That I have said that before. Therefore, you don't add a penny to the wealth of Bill Gates. However, if you have only $50, so maybe you want to say I have $50 and take 75 cents. That's a big number there. Is that correct or not? You see what I'm talking about? These two numbers compared to this original number are too small and is going to be eliminated. Is that understood? So there is no way. So don't do it this way, please. Do it the way I'm following there. Both, actually there is an area which rarely we use, but the volume definitely we use because it has application. I will tell you when you store oil or the silos and wheat and that, the volume is going to change. Is that understood? No, this is the way we do it. We do it based on epsilon. So let's take that. This is in your handout. Please open your handout. If you don't want to write it down, write it down. It is in your handout, page 11. So if I use a 1-by-1 unit at the beginning, before the loading, if I am loading after the loading, that becomes a little bit larger. Now, how much larger? One becomes 1 plus epsilon x, and the other one becomes 1 plus, because epsilon x and epsilon y are the amount of change per one unit. So one becomes 1 plus epsilon x, the other one becomes 1 plus epsilon. This is the new area. This is area new. And this is the original area. Yes or no? Correct. Now I can subtract this from. So now if I calculate the change in 1 unit equal to, this is what we did. This is only 1 unit because 1-by-1 is 1 unit. 1 is square inch, 1 millimeter square, etc. Et so that becomes 1 plus epsilon x multiplied by 1 plus epsilon y minus 1/1. Then we expand it. This we get 1 plus epsilon x plus epsilon y plus epsilon x multiplied by epsilon y minus 1. Now this one and that one drops out because it goes there, and I get these 3 numbers. However, epsilon x is in the order of 1/1000. Yes or no? Yeah. Epsilon times epsilon become on the order of 1/1000. A million, yes or no? That's too small. Compared to these two numbers, this is very small. We are going to assume that is negligible. Therefore, the change in the 1 unit become epsilon x plus epsilon y. That's it. Yes or no? So we use the epsilon. Now I can add these two together because they are at the same order. They are penny. So I can say 2 penny plus 3 penny is 5 penny. 2 plus 3, 5. But I cannot add it to the billion. Everybody under how many? 56 billion and 2 penny. Who wants to do that? Is that correct? Everybody see what I'm talking about? Now if I want to calculate the change in the area, now this is epsilon x plus epsilon y is the change for 1 unit. How many units do I have? 10 times 8. Everybody understand? So I multiply it by the area, original area. That's it. Now I get a valid number, so we'll see that. Similarly, the same thing for the volume, which has a name actually. So if you have a volume, the only difference is you have a volume of 1 by 1 by 1. It is all in your handout. You don't have to worry about it. And then you have here 1 plus epsilon x, 1 plus epsilon y, and 1 plus epsilon z. We did the same thing. We just subtract. This has a name on it. You get the change. This is E. There is a name. This is the mathematical name. You have to learn that. E is the amount of change for, write it down. E is the amount of change for 1 unit of volume. E, small e. The capital E, the modulus of elasticity, my friend. This is a small e. Small e is the amount of change per 1 unit of volume. The same, exactly, become the same. 1 plus epsilon x, 1 plus epsilon y, 1 times 1 plus epsilon z, minus 1 times 1 times 1. We do the same thing. It's done in your handout. E similarly become epsilon x plus epsilon y and epsilon z. So it becomes the 3 epsilon, when they added together, actually become equal, assuming that epsilon square are eliminated. Remember that. So that becomes the amount of change for 1 unit of volume. Notice when you have a storage coming from tanker and you put it in the silo and the big tanker there, the volume is going, because they are going to press each other, the volume is going to change a little bit. Or the same thing, you have the silo with the wheat, when you bring a truckload, when you put it there, you assume, sometimes there are this old timer, this is always the peasant will get the blame, because the Lord always were thinking they are bringing less load. Because so we work on so many loads, we put it in the silo, it goes down. Everybody says the volume become the measure on the silo is less than the measurement when they are coming with the donkey load. Is that, everybody understand that? And that's the change. So now let's go here and calculate the change in the volume. Usually we don't do the area, but if I want to calculate how much change do I have in this plate, in the volume of that plate, what do? I add epsilon x to, this is the way you do it. You don't measure, you don't do it this way, either way. You don't add this number to the length. Everybody understand that, please. That's a no-no. If you do that in your quiz, at your homework, you will not get the right answer. So, but here, epsilon E, the amount of change for 1 unit is epsilon x. What was our epsilon x? It's all sitting there. So what's our epsilon x? How many micro was it? 1,750 micro. What was epsilon y? You have it there in front of you. I want you to double check that we get used to that. What's epsilon y? Was equal to 500, and then epsilon z was minus 750. That ends up to 1,500. That result. So you come 1,500 micro. And then you calculate change in the length equal to 1,500 micro, which is 10 to the power of minus 6, multiplied by original volume. What was original volume? Is 10 times 8 times 2. Is that correct or not? Yes, that's the way we do it. 10 times 8 times 2, which become 0.24 inch to the power of 3. This is inch. So we calculate first the unit, and then we multiply it by the volume, like the density I was talking about. E is the amount of change for 1 unit of volume. Yes?
Just logically speaking, it's possible that all of the epsilons...
All of them become positive. Yeah. No, it's not positive. No.
It's not possible, so one of them has to be...
Negative, of course, yeah. Because when you put tension and tension, the other side become smaller. Yes. Unless you have sigma z, that's the difference. That's why they want to do that. So far for this one, no. No.
are.
That's right, yeah. If you are under, so if the sigma x, sigma y, sigma z are negative, then there are all three of them negative, yes. But that's the 3D problem, not for 2D. Okay? Not for 2D, yes? All right, now let's talk about something new, guys. So these are all fine. So far we talked about, the only thing new to this one after with this, what we talked last time, so I'll leave it there. The only thing was new is what just does how to calculate change in the area and change in the volume. That was the new. The rest of it, we are. Now I'm going to talk about something else, please. These are very important. What are these epsilon, guys? One more time, explain it to me. They are in the form of the expansion or shortening. That's what we are talking about, yes or no? They are called normal strain, something that may or may not, you paid attention. I keep saying that. I hope you have writing there. Look what happened here. Sigma x, epsilon x, e, then we went to the new, yes or no, correct? Then, of course, there was a, now I'm going to put into, what is this? This is normal stress. This is normal strain. As the result of this, then we have epsilon y, epsilon z, etc., and all of this were introduced. We never talk about the shear stress. Yes? What happened to the shear stress? What do we do if we have shear stress? Remember, we may have now, so please write it down. Now this is a new idea, totally new idea. You haven't heard it. These are shear stress. So let's put it this way. Shear stress, we know it is equal to tau. Remember, tau was equal to force over area, correct? What is shear strain now? This is the question we want to answer. All of them were related to sigma. Look, it was sigma x, sigma y, and sigma z. As I said, we don't go to sigma z, but generally that's what we do. Is that correct or not? So those are normal stresses, normal strain, modulus of elasticity, and nu. What happened here, we have to define a new strain for tau as well. Is that correct? So it is simpler. It's not as expensive as that. It's much shorter. That's why we can do it all today. This is, again, a stress element, one of the elements that we showed you, or a plate, or whatever you call it. This time, I'm not going to put it under sigma. I'm going to put it under shear stress, yes or no? Shear stress tau, remember, when I mentioned it last time, I showed you to you tau xy always equal to tau yx. Is that correct or not? Therefore, when I put here tau xy, I have to put here a tau yx as well. Is that correct? The two I said are always equal. That's why we have to go like this. And this was a positive format. I show you to you. I said this is a positive format, so discussion is always positive, but in reality, this is sometimes positive, sometimes negative. As the result of this type of loading here, let's assume this is kind of load. Do you think this is going to be expanded like the other one? Remember that one? We were stretching it or shortening it. This is not going to happen. This is a square. Let's assume this is a square body. After deformation, wouldn't you think that this is going to get, this is an exaggeration, to end up into a rhombus, because this two head goes together, this two head goes together, it becomes an angular change. So that angular change, so a shear strain actually is equal to angular change, and that therefore it becomes much simpler than the other one. These are all expansion which are going to affect each other. So look at it. When I had epsilon x, because of Poisson ratio, I created epsilon y and epsilon z because they were changing. This is the same because it doesn't matter this way or the other way. So it's all the same. But this is the fact that this angle originally was 90 degrees. Now it becomes 90 minus gamma. That gamma is called shear strain. So angular change, and we are showing it with gamma. Gamma is called shear strain now, okay? And it is very simple. Don't worry about this picture. It looks, of course, this gamma is very small. Don't assume if this is 90 degrees, now suddenly this becomes 60 degrees. That gamma is minute. Everybody says it's less than even 1 degree or half a degree. Everybody see what I'm talking about. That gamma is very minute, but it is there. It's a very small quantity. And this is what we want to do afterwards. So if I draw, remember the Hooke's law here? The Hooke's law here, I'm going to put it there. The Hooke's law for this operation was sigma versus epsilon. Remember that? Yes, when I plot that one, I don't have to do it again and again. We went like that. Then we got sigma yield. Then we had a little bit of stretching. Then we had the sigma ultimate. Then the necking there. So I asked you to read the rest of it by yourself. And that angle was what? That angle was modulus of elasticity, which gave us this equation. Right? So in this triangle, this was sigma, this was epsilon. Then we write tangent of that angle, which is the E, equal to sigma over the epsilon. We end up epsilon to be equal to sigma over modulus of from Hooke's law. Now we have to do the same thing here too. That this time, write it down, guys. We don't have to do, we have to do, this is a stress. So actually, this is a stress versus a strain. This is what they call it. Actually, they don't call it sigma versus epsilon. This is a stress versus a strain. I have to do the same thing here. There. Yes? Stress versus a strain. But what is my stress this time? The stress this time is not sigma. It is tau. What is my strain here this time is not E. It is not epsilon. It is, I just show it to you. It is gamma, yes or no? So that is the gamma, we put it here. If we do this, we get a rod and we do put it twisted, which we measure gamma, etc., etc. You don't have to go through detail of that. But however, we'll do the same curve. This curve goes up like that, like the other one. But this angle is not called modulus of elasticity. It is called modulus of rigidity, but we are showing it with the G. So therefore, you have to have here a G, which is similar to the E here. Remember, that angle was E. Now that angle becomes the G. So the same relationship exists here. So if I put down new idea there, I'm going to put it underneath here. This is tau xy. It's going to give me gamma. We have modulus of rigidity. Fortunately, we don't have a nu there because the two are the same. Everybody understands. Therefore, it becomes very simple. So it does not affect the other side. So we have only one relationship, and that relationship comes from this triangle again. This triangle, if you look at that triangle, this is tau, and that is gamma. Yes or no? So the G, so tangent of the phi this time become G modulus of rigidity, and that tangent of that angle equal to tau over gamma, or gamma become equal to exactly like that, tau divided by modulus, exactly like before. Strain equal to stress divided by modulus of rigidity this time. Exactly the same format. Remember here we end up, I put it here. Here we end up eventually from Hooke's law, we end up epsilon x equal to sigma x over E. Here we end up gamma, and then we end up gamma equals, or gamma xy we better call it, equal to tau xy divided by modulus of rigidity. It is very simpler in operation. It is useful in many ideas when we have to put, we'll see that in a minute. So what we have to do, use this method is this. Basically, this is the idea. Aside from this and this, which gives you the relationship, you should look at one more idea here, then we can go through example. Let's say we have a type of material which has a small g, therefore it can move back and forth. I will give you many examples here. So you have this one goes like that. This is before deformation. Let's say I applied here a shear force on top of that one. So it's going to end up to something like that. Is that correct or not? After the, so the bottom part is fixed to the floor, the top part moving there. This is your gamma. Please write it down. That's your gamma. And this distance from here to here, we call it delta. And this distance from here to we call it T, or the thickness. So anytime you have, let's say that this is what we are supposed to do in future. I give you one example, then I give you numerical example. So let's say that you are building how many civil engineers do we have here? So many, maybe perhaps. Okay, good. Let's say you have, next time you pass any bridges that you see, actually every time I go 605, I look on the bridge, I see this. On the bridge, you will see that pad, leopard pad. Let's say that there is a concrete beam here. comes and you want to put it on the column here. See this is the column there. This I just show you systematically. Is that correct or not? Yes? If you put this concrete over the concrete, of course, this concrete, because of the movement of the truck, because of the temperature, this is a beam, is going to move constantly back and forth. Every time a big truck there take a break, it will move this way. There is the earthquake forces, there is the temperature forces that causes that top one move back and forth. And if you put concrete on the concrete, it's not going to work. Immediately, it's going to crack. Is that correct? As a matter of fact, just to mention for the other class, one of the earliest projects that I did, it was a big stadium with a cabled roof, one of my earlier projects back 30, 40 years ago. And then the whole column, because of that, the contractor didn't do a good job of here connecting these two together. All the column were cracking. You could see it from the others. So it was useless. I don't know, it was about $300 million project, and they could not use it. They had to stop it, and we have to get a contractor. I got a contractor from England, which was very famous. They raised the whole stadium on the jack, and then built again those, corrected that. By doing this, by putting here a piece of material, we call it like that. This is the same. Is that correct? And that material can go back and forth. If you go under the bridge, next time look, but be careful not to get into the accident. I don't want to be caught a car. Look up, if you are in the traffic jam, you will see those pads there. And when the steel beam is sitting on the concrete or vice versa, is our concrete over the concrete. So you see this pad. Now this pad has a potential, having low G potential of moving back and forth, which concrete doesn't. Concrete is a rigid body, so it cracks. So if you don't use the right pad, so that pad smashes, so it put the concrete start cracking down. Is that correct or not? That got excessive load. So now let's go to example. So in this example, I changed it a little bit because the data in the book is not correct. And, oh, by the way, here I have to use something here which is very important. You want to alter that. Here we say tangent gamma equal to delta over T. Why did I use that one? Anybody know what I use tangent gamma equal to gamma? One of the reasons that they book the theta in your solution manual is because of that. They use tangent of theta instead of tangent theta. And if you read the book and you use that, follow that one, I believe you did not understand it. Because theta is very small. It has to be, otherwise it doesn't work. Now I want you to take your calculator, everybody. Please take your calculator without exception. Take your calculator. Everybody quickly, it's worth doing it. Because the answer, I got the right answer. If theta or gamma is very small, we can use tangent instead of theta. Yeah, why? Now it's the proof. Take 2 degree, guys, 2 degree, and convert it into radian. Take the 2 degree, convert it into radian. Tell me what you get. You get 0.349, something like that, what we did before that. Is that correct or not? Now take the sine of 2 degree. Sine of 2 degree is 0.0349. Is that correct or not? Yes? Take the tangent of 2 degree. Equal to 0.03. You don't have to do it. I write it down here. Yes? They are all the same. Everybody. Because theta or gamma is very small. So it is less than 2 to 2.5 degrees. That's what happened. And these angles are all less than, should be less than 2 degrees. It's more than 2-3 degrees, then this formula doesn't work. So you have to use tangent. Everybody understand? And that's why they use theta in your solution manual. I hope some of you did understand it. I don't know, or read it somewhere, but some of you probably didn't. That's why theta came out to a very large number. You accept, some people, one person came out to 74 degrees. Okay. So if that's 74 degrees, how did you use that formula? Everyone see what I'm talking about, because they used the wrong unit. Is that correct or not? So these are all related to each other. This gamma is very small. Remember that? So I can use tangent gamma instead of gamma. Is that correct or not? Or gamma? So that's what we are going to use. Now the next homework is this one, guys. Here is the I-beam, or this is beam that continues there. And let's say sitting on a concrete column, and they have put here the same, they call it elastomeric or Neopon type material, which you can go in the market, buy them separately with a different G value. So this material, we are talking about this material sitting there. I'm going to show the dimension of that one. There is a force here, P equal to 5,000 pounds, apply to this. You see the action of the temperature, the action of the earthquake, the action of the truck braking, or everything causes horizontal force. Horizontal force causes the beam wants to move on top of the concrete, and I cannot put the concrete on the steel or concrete over the concrete. Everybody, concrete over concrete is the worst. Is that correct or not? Yes, because it's going to crack. We have to put we have here also an expansion joint between here and the next one, which tolerate this. This goes back and forth. In other words, I'll show you in a minute. So therefore, that pad has the following dimensions. So please write it down. This in the book, they say this is B from here to here is B, but I show you here a little bit better. So that pad has this kind of dimension. This is B, this is 8-inch. And in the book, they call this one A, but I rather you call it thickness of that pad or the height of the pad, or that's okay. That's it. Yes? That's the little piece of material like this, which you put it here, like that. Here, is that understood? Yes? The data that they have given is the following. P equal to 5,000 pounds, so we already have that. Tau for this material cannot exceed tau allowable. Cannot exceed 60 psi, because that's a very soft material. And what else? The tolerance that the movement of this pad, the delta of the pad, should be less than 3/8 of an inch. You know what that means? That means that there is another beam coming here, that the gap between the two should not be more than 3, because if it's more than, they are going to hit each other. Is that correct or not? So they put usually a gap there, expansion joint we call it, and that gap is less than 3/8 of an inch. Is that, or should be maximum 3/8 of an inch. So those are the data that have given to us. And what else? That's it. Oh, okay. 3/8 of 60, that's it. Now we want to calculate the B value and the thickness or A value. That's the same thing. We want 2 dimensions here. In other words, what kind of block should I buy to put it there to tolerate this movement, 3/8 of an inch of movement. Yes? All of it you have, no. First of all, this is the shear stress, yes or no? So notice what happened here. If you took a free body diagram here, I'm going to do it like that because it's faster and sorry, you cannot erase yours. Notice what happened here. There is a 5,000 force here, P, but here it becomes a shear force. On top beam, it goes this way. On the lower one, it goes that way, yes or no? So we have here that on the pad, on top of the pad, we have a shear force of, as you have seen it before, shear force of V, and A is equal to 5,000 pounds. That's the shear force, yes or no? So everybody can calculate the tau now. Tau equal to what? Tau equal to force over area. That is lecture 1. Is that correct? That's why you have to relate to it. See, this doesn't give you anything that you have to put everything together. You have to understand it, in other words. You cannot superficially pass the equation and say, oh, I'm done or finished. You have to put everything together. All of this already be done. So there is a shear stress here on top. That shear stress tau equal to what? We did it in the past. Equal to force over area. What force do we have? 5,000 pounds. What area do I have? Area is, if it was given, if this was, let's say, 20 inch by 8 inches, I put it there, calculate the tau. But the question is, B is not given, times 8 inch. B inches times 8 inches. Yes or no? However, this tau should not exceed how much? 60 P. See how the things come together? These are the thinking process. It's not something that you can remember from one action to another. It's the meaning of tau, meaning of the shear force, meaning of this and that. It's that very simple operation. However, you have to do it. You have to practice. That should not exceed 60 pounds per inch square. Pound per inch square. So immediately I calculate the value of the B. The value of the B ends up to be equal to 10.42 inches. Of course, you just go by a foot of that or something a little bit bigger. You have a factor of, because you already have using tau allowable anyhow, factor of safety is there. So at least it should be 10.5 inches and above in order to work for you. Yes, that's one item. The other item is what thickness should I use for this one? The thickness, of course, is related to delta. I already showed you. Look, see that relationship? Everybody see that? That the relationship, you have to use it there. Already there. Because this after deformation it's going to end up like that. Is that correct? Because this beam wants to move that way, pull the pad. This column is sitting there. Is that correct? So the top of the pad is going to move. The more rigid it is, the more resistance is shown. Is that understood? That? But this is the flexible material, correct? That's why it can go more. Concrete cannot go that much. Everybody, concrete goes 0.01 inch. Is that understood? Yes? Remember all the deformation we were calculating was less than 100 of inch around that area. But this is a plastic material. It can go. That's why you have, by the way, that's why you have between the glass and the steel there, you have a caulking there. Why do you think the caulking is there? Caulking because the temperature, the glass and the aluminum defend differently. If you don't have it, it's going to crack. You put a flexible material, that flexible, we call it caulking. Yes or no? You have your dryer. Everybody has a dryer at home. Yes? You have the pipe going through the wall. You always see a crack around it. Yes or no? Why? Because the temperature changes. So you have to put a caulking material there. That caulking material, you push it back and forth without you seeing the crack. Is that correct? So that's what many things, many applications. Any engine you have, you cannot connect the engine to the ground because the engine is going to vibrate. So you have to put a pad underneath in order to take the vibration out. All of that related to the same thing here. This is moving to the right and left, depending on changing of the loop. Anyhow, then make it the story short, you have to go faster. So here we go, the last part of it. And the last part of it is actually this type of problem. I'll give you only two, and it's very simple. Just there are always a plate between two plates, so it moves up and down or this way, so you can use the same technique. So now here we go. So, sorry. So here it is. This is the pad. This is the thickness or A. And this is how I'll show you a little bit more exaggeration. This is the gamma, and that is the delta. That delta is given 3/8 of an inch. We cannot want to move it more than 3/8 of an inch was given here. Yes, sir. And then I need the gamma because there are two. Now I can write tangent gamma equal to delta over t, or delta is equal to 3/8 of an inch, but over t. I'm looking for t, so I must find gamma from my data. Yes or no? Correct? Because the question is, what is A or T? Everybody understand that? So our gamma comes from here. Where is the gamma coming from? I gave you the formula. Gamma coming from tau over modulus of rigidity. Exactly. That's like before. You see, that's what I was insisting you guys to use this equation, not delta over L. Because if you use this one, you get used to it. Everybody understand that. Epsilon equal to sigma over modulus of rigidity. Here it is gamma equal to tau over modulus of rigidity. The same formula, but the same format. There's nothing there extra there. So therefore, since gamma is equal to tau over modulus of rigidity by definition of the Hooke's law, therefore gamma become equal to tau. How much was tau? 60 psi, correct or not? Divided by G. G was given to you. G was, oops, I didn't give it to you. I'm sorry. Oops. Actually, G is the one I changed. In the book, they said 130. 130 is too low. It doesn't work for this problem. I changed it to 1300 psi. So please write it out. I changed it to 13, because otherwise the gamma become too large. So therefore, I changed it to 1300. So I'm sorry for that. So you put here 1300 psi. So that's psi over psi. So it becomes 0.0462. Notice it's still a small number, but we are going to go 3 digits. Some of you are not following. Next quiz, I'm going to subtract point there if you do not follow the minimum of 3-digit accuracy. Everybody understand that. No matter how number is big or number, you have to have minimum of 3 digits. Anyhow, that's your gamma. You put the gamma there. You calculate the value of t. So 0.0462 must be equal to 3/8 of an inch divided by thickness of the t. Thickness of the t become equal to 8.113 inches. So you have the pad like that. I presume we are out of time. Yes or no? Yes? Oh, but I have to give you one more hint. Otherwise, you cannot do your homework. So there is one more problem that unfortunately I was going to do, but it is very simple, but I'm going to mention it here. Let's go back. Just give me 2 minutes, guys. 2 minutes, sorry. Without that, if you want to leave, go ahead. But this, you cannot do your homework without me mentioning this. It is very fact that here is the same plate I had before. Remember, this was 10 inches by 8 inches. And let's say that I put this under a compression stress of 20 KSI. This is sigma. Yes? If I put this sigma here, this or nothing else, it's going to expand that way and going to expand the other way because this is compression, so it's going to expand that way, expand that. It is free, yes or no? However, some of your problems are like that. So if I put this top one between two rigid bar or plate, that there is no movement in that one, what's going to happen? This side is free, only the top one. I'm putting this on top and the bottom, and I'm pushing this way. What's going to happen? This side wants to expand, but you are not letting it expand. Therefore, the delta and epsilon in the y direction is 0. Yes or no? However, since it wants to expand, in other words, if you remember the superposition method, if you let it expand, it goes up, then you have to push it back. That's one way of doing it, which is a wrong way of doing it, but use the epsilon here. Look, there is an epsilon here, yes? There is an epsilon and z, but epsilon in the y direction is 0 because it's between two walls, is not going to that. Therefore, in this problem, epsilon y, let's call it y. Epsilon y is 0 because there's no movement. This is y direction, x and y. Is that correct? Yes? Since epsilon y is equal to 0, therefore it wants to go there. You are pushing. There must be a sigma y there, and you don't know the magnitude of that. Yes, or you have to find the sigma y first. So it becomes like the problem I did. Is that correct? But sigma y, there a sigma y was given, is sigma y is not. However, you can use this one. What was epsilon y equal to 0? Look at it. I'll go there. Way. If I put epsilon y equal to 0, look at it. What happened? E and E going to drop out. There is a relationship between sigma x and, if I'm giving you sigma x, can you calculate sigma y? Yes or no? So use that. Use the epsilon. So anytime you have a rod which is restricted or a plane restricted in certain direction, epsilon in that direction, set it equal to 0. That gives you the extra equation for your extra unknown. Then you find it. That's the way we do it. And hopefully I will get a chance to do it on Thursday. I'll let you know what happened or which homework. There are 2 homework at the end, 93.